Welcome back to the deep dive. We are doing something a little unusual today.
A little bit, yeah.
Usually we're tearing apart a complex history or some new piece of tech, but today we are looking at a single page of text. It's labeled simply Lesson 1, Even and Odd Exponents of a Negative Base.
It sounds incredibly dry. I know it does. It sounds like something you'd find crumbled at the bottom of a high school locker.
That is exactly what I thought. I looked at this source material and thought, okay, basic algebra, I know this.
Why are we talking about this?
Exactly. But the more I read through the specific warning sections, and we will get to those, the more I realize this isn't really about math.
Not at its core.
It's about reading comprehension. It's about how a tiny curved line, a parenthesis, changes the fundamental reality of a number.
It's the difference between a number existing and like a command being executed.
Yeah.
That is the level we are operating on today. It's syntax.
So, our mission today is to decode this. We're going to break down how negative numbers react to exponents, sure. But more importantly, we're going to identify that specific visual trap. The one the source material warns is the most common cause of error. And honestly, it's a trap I think I would have fallen into before reading this.
Oh, most people do. It is intuitive to get it wrong, which is why you have to kind of retrain your brain a bit.
So let's start with the landscape. The source sets up a scenario. We have a base, and that base is negative. Call it negative A.
Right.
And we are raising it to a power.
Right. So picture -3 or -5, and you have that little superscript number hanging off to the right. The document basically divides the entire universe of outcomes into two buckets.
Based on that little number.
Is it even, or is it odd?
It feels very binary. It's essentially a flowchart.
Math usually is.
Yeah.
So let's look at the first bucket, the even exponent. 2, 4, 6, 8.
The rule here is the one most people sort of remember from school. The source says, open parenthesis, negative A, close parenthesis, to the power of m equals A to the power of m. In plain English. If you raise a negative number to an even power, the result is positive.
Correct. But let's pause there for a second. Do you know why the source says that happened? It uses the example of -3 in parentheses squared.
Well, I assume it's just, the rule of doubles. -3 multiplied by -3.
It is. But think about the mechanics of it. In multiplication, a negative sign is basically an instruction to flip direction on the number line.
Okay.
The first negative flicks you to the left side of 0. The second negative flips you right back to the right.
So they cancel out. It's like a double negative in language. I am not going.
Meaning, I'm going. Exactly. Cancel is a good word. Or neutralize. Since an even number is always made of perfect pairs, every single negative sign has a partner.
There's nothing left over.
Nothing. The result is +9.
The source calls this the simplest form. It is satisfying, it's clean. The negative sign it evaporates.
Well, it doesn't evaporate. It resolves.
Yeah.
And that's an important distinction. The calculation consumed the signs.
Okay, fair enough. Now let's look at the other side of that chart, the odd exponents. 3, 5, 7.
Here, the symmetry breaks.
The rule they give is that negative A, in parentheses, to the power of m equals negative A to the m. So if I raise a negative number to an odd power, the result stays negative.
Walk through the example they give. -3 in parentheses cubed.
Okay, so that's -3 times -3 times -3.
Right. 3 times.
So the first two do what we just talked about. -3 times -3 is +9.
But they resolve.
But you aren't done.
Nope.
No, I still have that third -3 waiting in line. So now I have +9 times -3. A positive times a negative is a negative. -27.
Exactly. An odd number is essentially just a bunch of pairs, plus one extra. That +1 is the survivor. It carries the negative sign all the way to the final answer.
So it doesn't matter if the exponent is 3 or like 3,000,001. If it's odd, that negative sign is basically bulletproof.
It rides the equation all the way to the end.
Okay. I feel like I get this. Even exponent, positive result. Odd exponent, negative result. It seems incredibly straightforward.
It seems that way.
I'm going to be honest. I'm waiting for the other shoe to drop here. Why do we need a whole deep dive on this?
Because you just described the happy path. You described the scenario where everything goes right. But the source material, it includes a section called Notice the Difference.
Ah.
And this is where the actual complexity lies.
Yeah, I am looking at it now. It puts two expressions side by side. On the left, it has -3 in parentheses squared. On the right, it has -3 squared.
And to a casual reader or, someone rushing through a spreadsheet, those look identical. I mean, if I read them out loud, I say -3 squared for both of them.
And that is why English is a terrible language for math. You said the same sentence, but you described two completely different mathematical operations.
Okay, walk me through the difference. The one on the left has parentheses.
Right. Think of the parentheses as a container, or like a property line. Everything inside that fence belongs together. When we put the -3 inside, we're telling the exponent, you are squaring this entire package.
So the negativity is part of the identity of the number being squared.
Exactly. You are squaring the concept of -3. That is why the negatives pair up and become positive.
Okay, now look at the one on the right. -3 squared, no parentheses.
Just a naked negative sign sitting next to a 3.
Yeah.
This is the trap. And this brings us to the single most important concept in this entire document. It is about scope. Exponents are incredibly short-sighted.
What do you mean?
They only affect the object immediately to their left.
So in the case of -3 squared, the little 2 is only looking at the 3. It doesn't even see the negative sign. The negative sign is standing one step away. The exponent just says, I have a 3 here, I'm going to square it.
So it calculates 3 squared first, which is 9.
And then after all the heavy lifting is done, that negative sign, which has just been waiting in the lobby this whole time, steps in and attaches itself to the front.
So the result is -9.
Negative and 9.
Wait, so even though the exponent is even, the result is negative.
Yes. And this is where people fail tests. They see an even number, and their brain just shortcuts to rule number 1, even means positive.
Right.
But rule number 1 only applies if you're actually squaring the negative. In this case, you aren't. You are squaring the 3 and then negating the result.
That seems, it seems almost pedantic, doesn't it? Like, isn't that just a gotcha trick designed to fail students?
It feels like a trick, I get that, but it is actually about the order of operations. You remember PEMDAS, parentheses, exponents.
Vaguely. Please don't make me recite it.
We will make you recite it. But just look at the order. E for exponents comes before S for subtraction or negation.
Ah.
So the math universe demands that you do the power, the 3 squared, before you apply the minus sign.
So the calculator isn't trying to trick me, it is just following a strict hierarchy.
Correct. And the only way to override that hierarchy is to use parentheses because P comes before E.
So the parentheses force the negative sign to be processed before the exponent does its work.
Precisely. Without the parentheses, the negative is just a bystander till the very end.
That is a huge distinction. +9 versus -9, that is an 18-point swing. In a financial model, that's the difference between profit and loss.
It's the difference between a bridge standing up and falling down. It's strictly structural.
The source pushes us to test this with example 4. It says find in simplest form. And I want to try these because looking at them now, they feel deceptive.
Go for it. Let's apply the logic.
Okay, first one. -5 in parentheses cubed, so parentheses are present.
Break it down. What's the base?
The parentheses mean the negative is in the box. So I am cubing -5.
And the exponent.
It's 3, which is odd.
And the odd rule.
Odd means the negative survives. 5 times 5 is 125. Negative stays.
Yes.
So -125.
Spot on. Since it's odd, the parentheses actually didn't change the sign outcome, but they did correctly group the number. Good grammar.
Okay, next one. -5 in parentheses squared. Parentheses are still there.
So the negative is still locked in the box.
But the exponent is 2. Even.
And the even rule.
Even means the pairs cancel out. -5 times -5, +25.
Correct. That's that sanitizer effect we talked about.
Now the third one. The one without the safety rails. -5 squared.
What do your eyes see versus what does the math logic see?
My eyes see -5 squared. My brain wants to say +25 because of the even exponent.
But resist the urge. Apply the order of operations.
Okay. The exponent is clingy. It grabs the 5. It ignores the negative.
Correct. Yeah. It has no jurisdiction over the negative sign.
So it squares the 5 to get 25, and then applying the negative sign, we get -25.
There it is.
It's wild because if I just glanced at problem 2 and problem 3, I would think they were the same answer. But one is 25, the other is -25.
They are opposites. And notice something interesting about the odd exponent example we did first. The -5 cubed.
Yeah, it was -125.
Okay, so what if I remove the parentheses from that one? What if it was just -5 cubed?
Okay, let's trace it. The exponent, 3, cubes the 5, that's 125. Then the negative applies. It's still -125.
Right. And this is why the trap is so insidious. With odd exponents, Sloppy grammar often gives you the correct answer anyway by accident.
You get lucky.
You get lucky.
Because the negative survives in both scenarios. If I'm sloppy with the brackets, the universe forgives me because it's an odd number.
Exactly. But with even exponents, sloppy grammar is fatal. The difference between notation types is the difference between positive and negative. You don't get lucky with even numbers.
That is a really scary insight. You can go through life with bad math grammar and get the right answer half the time, just by chance, until you hit an even number and everything just breaks.
That is why the source emphasizes this distinction. It's not enough to know the answer, you have to respect the notation.
So zooming out from the arithmetic for a second, we have spent a lot of time on these specific numbers. What is the takeaway here for someone who isn't taking a math test tomorrow? Why should we care about this level of syntax?
It comes down to clarity of instruction and the implications of understanding the system you are working in. I mean, in the modern world, we interact with algorithms constantly.
Right.
Excel, Python, even the calculator on your phone.
They all follow these rules.
Rigidly. If you type -5 caret 2 into a spreadsheet, it'll give you -25.
Every time.
Every time. If you meant -5 squared and wanted +25, but you didn't type the parentheses, your data is just corrupted.
And the computer won't flag it as an error.
No, because it isn't an error in calculation. It is an error in communication. The computer isn't smart enough to know what you meant. It only knows what you typed.
It is a lesson in precision. The even power rule, that magic trick that turns negatives into positives, it's not a blank check. It has a condition.
The condition is the negative sign inside the house? If it is outside, the rule doesn't apply.
I think that is going to stick with me. The idea of the naked negative being vulnerable, or rather being excluded from the operation.
Excluded is the perfect word. It's just waiting its turn.
You know, we have spent this whole time talking about a few inches of text on a worksheet, but it feels like we've uncovered a philosophy of logic.
Well, math is a language. And like any language, punctuation dictates meaning. Let's eat grandma and let's eat grandma are very different sentences.
Right.
Entirely dependent on a comma.
Yeah.
This is the mathematical version of that.
That is a disturbing but very accurate analogy.
You won't forget the comma now.
Definitely not. Well, that brings us to the end of this deep dive into Lesson 1. It turns out the devil really is in the details, or in this case, the parentheses.
Always check your brackets.
Before we sign off, I want to leave you with a thought. We tend to think of math as something that exists naturally in the universe, right? Like gravity. But this rule we talked about today, the order of operations, the way a parenthesis changes a value, that's a human invention. We decided on the grammar. We built the box. It makes you wonder, how much of truth is just us agreeing on the rules of the game?
And if you don't know the rules, you can't really play the game.
Keep your eyes on those naked negatives, everyone. They are lurking. Thanks for listening, and we will catch you on the next deep dive.